On to our calculations here. Isotope notation. What we need to do is know that the mass number is equal to the atomic number, or let's simplify this, number of protons plus the number of neutrons, okay? So, what we do here is this. We want to know how many protons, neutrons, and electrons are in one isotope of gold 197, okay? So, we first start out with the number of protons. Remember, the number of protons is equal to the atomic number, all right? So what we do is we look up gold, AU, we look up gold on the periodic table. So if we look up gold, I'm just using the periodic table in the book, we find gold has an atomic number of 79. So we write down 79 because the atomic number is the number of protons. Now, like I said before, unless I specifically state, we're going to consider all atoms neutrons. So the number of electrons and protons are equal. So that means because we have 79 protons, we have 79 electrons. Now our neutrons, we're going to have to do a little bit of work. And so that is this. Our mass number, which is 197, is equal to the number of protons, 79, plus our number of neutrons. So to find out this information, what we have to do here is we have to take 197 minus 79, and we get 118 as our number of neutrons. All right, so what I want you to do here is this. I want you to attempt part B on your own. I'll pause the video, give yourself some time, and then I'll show you the answer. All right, so these should be your answers for strontium-90. 38 protons and electrons, and then 52 neutrons. All right, so the second question here says magnesium has 3 isotopes with mass numbers 24, 25, and 26. We want to write the complete chemical symbol for each. All right, so what we would do first is we would look up the atomic number, which is the number of protons. We find here on our periodic table that magnesium has an atomic number of 12. So magnesium, I'm going to write this out to the side here, has an atomic number equal to 12. That is going to be important because with our 3 isotopes, we have to identify that. So our first isotope here with magnesium, I'm just going to write number 1. We're going to write Mg for the symbol. Then in that upper left-hand corner, we are going to write 24 for the mass number, and then 12 as the atomic number or number of protons. We are then going to do the same thing, but for the isotope with a mass number of 25, written in that upper left-hand corner. We write 12 to represent that we have 12 protons, or an atomic number of 12. And then for that third isotope, we start out with the symbol. In the upper left-hand corner, we have the mass number of 26 and 12 as our atomic number or number of protons. Now, it's also important to write this in our other notation and that other notation would just be writing out the name dash the mass number. So again, it's important to have each of these just so we become familiar with how do we write those isotope notations for each. Now, it says down here how many neutrons are in each of those particular isotopes. So I fully expect you can do this on your own. I'm going to pause the video, write them out so you have the answers as well. All right, so there are your number of neutrons for each of those three isotopes respectively. All right, so now what you may be wondering is this. All right, in chemistry, I really have never seen these isotope notations. And that's probably true. Rather than introduce the specific isotopes, we deal with an atomic weight, which is a special unique average of all of these isotopes of one particular element. And that's generally what we see rather than dealing with all of the isotopes an element may have. So it's important to know this so that we can identify that isotope and how many protons, neutrons, and electrons, if we go through that calculations, they have. But it's important, okay, real world chemistry, why don't we typically see our isotope notation? Now, there's specific branches of chemistry that deal with the isotopes more than others. One in particular is nuclear chemistry that deals with that business there. All right, so we get into this idea of atomic weights. And we start out here with the atomic mass unit. So an atomic mass unit actually has a direct definition. It is equal to this value here, which I'm not too concerned about, but this value right here, 1 AMU or 1 atomic mass unit, comes from a carbon-12 isotope. What they did is they divided it into 12 pieces, or they said a carbon-12 isotope has exactly 12 AMU. So that's where they got this basis of the number. Now, they used to use hydrogen, but some numbers got controversial there. So carbon-12, the carbon-12 isotope, is where we get the definition for 1 atomic mass unit. Now, we're going to get to this thing that the book likes to call the atomic weight. I like to call it the average atomic mass. And let me make that note here. Sometimes I'm going to call this the average atomic mass, because it is a mass, and when we think of weight, we are thinking of a little bit different measurement that we have. Again, a better term here would be that average atomic mass. Now, why do we get a decimal number? We just dealt with isotopes that had equal number of protons and neutrons. Well, let me tell you, we cannot break or divide a proton or a neutron without altering the element that we're working with. So let's turn the page here. Let's turn the page. And let's get to how exactly we calculate the average atomic mass. Okay? So, number one, the average atomic mass is the average of masses of isotopes. Now, again, what I want to put is isotopes have whole numbers of protons and neutrons. Okay, you cannot have a proton that's cut in half or a neutron that's cut in half. You have to have whole numbers. The number that we see down here on the periodic table, that average atomic mass, is a unique average of all the isotopes of that particular element in the whole universe. But what we do to do this is we take the percent, and we take the percent and we convert it to a decimal form. We multiply it by what the particular isotope mass is, and we do that for each and every isotope that we have. Once we've done that, we add those calculations that I just described above, and that addition becomes that atomic weight. So that is how they get the average atomic mass that we see on that periodic table. So let's go ahead, let's go through an example of this particular steps to calculate the average atomic mass. All right, so here we go. We got chlorine. Chlorine has two naturally occurring isotopes, chlorine-35 and chlorine-37. Each has a particular percent abundance in the universe. So to calculate the atomic mass of the chlorine, what we do is this. We take the percent of isotope 1. So I'm going to take 75.78%. And I'm going to convert it to the decimal form. And so the way in which we do that is just we divide this by 100. So if you need to see it in the calculator, we take 75.78 divided by 100. We press enter, and we get a decimal of 0.7578. So we take 0.7578, and we multiply it by the atomic mass of that isotope. Now that atomic mass is given at 34.969 AMU. So I'm going to write that exactly down, 34.969 AMU. Now, I'm going to perform this on my calculator. 0.7578 times 34.969. I press enter, and I'm going to write down as many decimals as we have here. So 3 decimals, so 26.499, and that actually rounds up to 26.500 when you round. So 26.500, again, atomic mass unit. And then what we do the same exact process for the other isotope. Now keep in mind, the other isotope has a percent abundance of 24.22%. We divide that percent by 100. So we have 24.22 divided by 100, and we press enter. That means we get a decimal of 0.2422. We multiply it by the atomic mass of that particular isotope. So we get an atomic mass of 36.966 AMU. Now I'm going to perform that calculation in my calculator. So I'm going to take 0.2422 times 36.966, and I press enter. I get a value here. I'm going to go to 3 decimals here of 8.953. Again, that's 8.953, and that unit on that would be AMU. Now, what we do here, I've already set it up, is we add these two values together, okay? So we take 26.500 plus 8.953, and we press enter. All right, so now what we do here is we write this value down, and so this becomes this becomes 35.453 AMU. And this right here is the average atomic mass of chlorine. And that becomes our answer. All right, so again, the key thing here is making sure we take the percent to decimal form and then we multiply it by the correct atomic mass for each isotope. Now, the percent abundance and the atomic mass will be given. Your job is to calculate these numbers and add them together to get your correct atomic mass. Now, I want to show you something real quick. That 35.453, what we just spent time calculating for the atomic mass of chlorine, is shown here on the periodic table. The value 35.453 is exactly what we have on the periodic table, and that's because that is the average atomic mass. They did a similar calculation to calculate this. Something else to note here is that the percent abundance can be found in the universe. They have some special calculations to take each isotope and figure out, well, what is the percent abundance of that isotope compared to all other isotopes of that element. Again, they have some special calculations that are very, very true, and they're very, very exact there. All right, so two more things that I want to talk about before we end notes here, and that